Hello dear friends, a great welcome to this series on engineering mechanics. Myself is Jayarajan P. This is class 4 of the series and covers the following topics. It essentially consists of short examples covering calculations for different topics that we have discussed in the last 3 classes. For example, it includes the computation of the resultant of two forces, calculation of components of a force along any two axes, expressing a given vector in a Cartesian format, and also examples covering direction, cosines, and unit vectors. So let us start our class. So let us start with example 1. So the problem statement is as follows. The screw I shown in figure A below is subjected to two forces, vector F1 and vector F2. Determine the magnitude and direction of the resultant force. So from the problem statement, it is clear that we need to obtain the magnitude and direction of the resultant force, which represents an equivalent to forces F1 and F2. So as usual, we require both the magnitude as well as the direction of these components. And here is shown a screw I, and F1 has got a magnitude of 100 Newton and it is inclined 15 degrees to the horizontal. So F2 has got a magnitude of 150 Newton and it is inclined 10 degrees to the vertical. It does mean that F1 and F2 are defined completely in terms of its magnitude and direction. So it does mean that we can straight away go for the construction of the parallelogram and apply the parallelogram law, and from which we can also construct the vector triangle and apply the law of cosines as well as the sines in order to find out the magnitude as well as the direction of the resultant force. So as you can see, the parallelogram that is constructed is shown here. So in the parallelogram, what is first to be drawn is you need to draw the adjacent side of this parallelogram, right? So what is done here is that, as you can see, first of all, one side of the parallelogram is drawn such that it represents vector F1. So it does mean that the length of this side will be 100 and it is inclined at 15 degrees to the horizontal. And next what we do is that we construct the other side of the parallelogram such that it represents in magnitude and direction the force F2. Means it has got a length of 150 units and it is inclined at 10 degrees to the vertical. Now what we can do is that we have the two sides of the parallelogram. For example, we can draw a line from the head of F1 parallel to F2. Also, similarly, what we can do is that we can draw a line from the head of F2 parallel to F1 and both these lines meeting at point A. Now, obviously, the diagonal of this parallelogram, it represents the magnitude and the direction of the resultant. So it is important here that we mark all the angles correctly, because the angles calculated must be good enough or correct enough to be applied for the sine rule and the cosine rule. So look here, for example, here we have got 10 degrees and 15 degrees already marked as per the directions of F1 and F2. This means that the included angle should be 90 minus 10 minus 15, that is 65 degrees. So the opposite angle should be the same, so 65 degrees. This means that the other two included angle should be nothing but 360 minus 2 into 65 by 2, that is 115 degree, considering that the sum of all the angles should be 360 degrees. Now it is very easy for us to construct a vector triangle from this parallelogram. Look here. So in the vector triangle, what you have to do is that we have to represent the two sides of the triangle, okay, by its components. For example, here I have drawn one side representing F1. Okay, that means the length of the side will be 100 units and is inclined at 15 degrees. And from the head of F1, okay, I will start the tail of F2, so that you can say that this side is parallel to by F2 and the length of the side will be equal to F2, magnitude of F2, that is 150 Newton. So remember one very important thing, whenever we use a vector triangle, okay, the vectors are to be added or to be connected in a head to tail fashion. Okay, so means that the components flows in one direction. Now obviously we'll be obtaining the resultant as the third side, and the direction will be drawn from the tail of the first vector to the head of the last vector as shown here. So we can easily obtain the included angles from, we can straight away take from the parallelogram and mark it. So now let us focus on this triangle. We have the two sides. This side representing 100 Newton and the other side representing the 150 Newton. And we know the angular angle between these two sides, that is 115 degrees, which we have straight away taken from the parallelogram. So we can directly go for the application of the law of cosines, which says that c square is equal to a square plus b square minus of 2ab cos alpha, where alpha is the angular angle. Applying this, we find that the magnitude of the resultant force Fr is obtained as 100 square plus 150 square minus 2 into 100 to 150 into cosine of the angular angle, that is 115. So we obtain the magnitude of the resultant as 230 Newton. So remember here that for this specific problem we find that the magnitude of the resultant is greater than its component forces, that is 100 Newton as well as 150 Newton. This may not be the case in every problem, okay, but this is a statement very specific to this problem. So we obtain the magnitude. Now what is remaining next is we need to obtain its direction. That means we need to find out what's the angle which it makes with the horizontal. That's our reference axis. So let us mark angle theta. That's the angle which Fr makes with my force F1. So let us start applying the law of sines. So applying this law of sines, which is A by sin A is equal to B by sin B is equal to C by sin C, we obtained as 150 divided by sine of theta is equal to 213. That's the resultant divided by the opposite angle, sine of 115, which means that theta is equal to 39.8 degrees. So we obtained the angle which the resultant force makes with the force F1, that's 39.8 degrees, which means that the resultant force Fr makes an angle of a phi, okay, with the horizontal, which is equal to theta plus 15 degrees. That means it makes an angle of 39.8 plus 15, that's equal to 54.8 degrees. So we have completely defined the resultant both in terms of its magnitude as well as the direction. Okay, so this first example clearly explains the application of the parallelogram law as well as the vector triangle in the computation of the magnitude and the direction of the resultant force. Now let me take you to example number 2. Example number 2 is exactly the reverse of example number 1. So let me first read the problem. Resolve the horizontal 600 lb force in figure A into components acting along the U and V axis and determine the magnitudes of these forces. Look here, as shown in figure A, you can see that two members are connected at a pin, and the pin joint that is common to the two members, it is subjected to a horizontal force of 600 lb, and the orientation of the two member axes are specified here. So as you can see that U axis is oriented along the first member and the V axis along the second member. So you are asked to find out what will be the magnitude of the components of this applied load 600 lb along the given U and V axis. So look here, both the orientation of the U and V axis are supplied in the problem. So here is a problem wherein we are given a resultant, that's a 600 lb force, and we are asked to find out its components along the U and V axis. So the procedure is very simple. So in this case also what we go is, we straight away go for the compilation of the corresponding parallelogram. Also we will extract a vector triangle from the parallelogram. So what we do is that first of all we draw our U axis. This is our U axis, okay, and as you can see that this is your V axis, and remember here the U and V axis, okay, the angle between them is very clear to us. So this is 30 degree, means that this the total angle should be how much? Should be 150 degrees, and this should be obviously nothing but 120 degrees. So we have the angle between the U and V axis, that's 150 degrees. So draw the U axis, okay, so the U axis is inclined at 30 degree to the horizontal. Now draw the V axis, okay, that is inclined at 120 degree to the horizontal. So now the problem is very simple. 600 lb, it is the resultant force. So given the diagonal, we are given the diagonal and we are asked to obtain the other two sides of the parallelogram. So it is very simple. What we need to do is that from the head of this vector resultant force 600 lb, okay, We draw a line first parallel to the v-axis, parallel to the v-axis. It meets the u-axis at the point B. Now it is clear that AB represents the component of 600 lb along the u-axis represented by FU. Similarly, what we do is we draw from the head of this diagonal, okay, a line parallel to the u-axis where it meets the v-axis at the point C. Then in that case, AC represents the component of the 600 lb force along the v-axis. So as you can see, yes, we have completed the parallelogram in which the diagonal is represented by the 600 lb force and the adjacent sides, okay, that is directed along the u and v axis, provides us Fu and Fv. And the vector triangle that is extracted from this parallelogram is shown here. And obviously remember that Fu and Fv are the components. So it does mean that you have to first of all draw one side of the parallelogram, okay, representing Fu, right? And then draw the other side that is representing Fv, and remember that Fu and Fv are the components. Obviously, accordingly they should be connected in a head to tail fashion, and the third side will be represented by the resultant, that is of 600 lb. And all these included angles directly you can transfer to the vector triangle, because we are directly go for the application of the law of sines as well as the law of cosines. Okay, so let us start the problem. So what we can do is we can straight away to this vector triangle, what we can do, we can apply the law of sines, right? If you apply the law of sines to this vector triangle, what we obtain is Fu by sine 120. This is my Fu divided by the A by sine A, that is Fu by sine 120 is equal to 600 divided by sine 30. Okay, so this is the application of law of sines, which is from which we obtain Fu, the magnitude of the component of the 600 lb force along the u-axis, as Fu is equal to 1039 lb. lb means pounds. And now, to obtain Fv, we apply the law of sine second time. That is, we have Fv by sine 30. That is, Fv by sine 30 is equal to same 600 by sine 30, which means that Fv equal to 600 lb. Okay. Now here in this specific problem, look here, our resultant is 600 lb, but its component is much higher. So don't be under the impression that the resultant will always be greater than the components. In this case, we find that Fu is much higher than the resultant. Fu is 1039, which is much higher than the resultant force of 600 lb. So the value of the component, obviously we conclude that it all depends upon the axis along which we are seeking the component, right? So this example will provide you what we call as an approach to obtain the components of a given force along any two axes. Obviously, you will find that there is a dot product approach also which we can use, okay, which you will see in the coming classes. So that's all about the problem number 2. Now coming to example 3. Example 3 provides you the ways or how to approach or what must be the procedure to be used in order to express a given vector in the Cartesian format. Look here. So here the problem says express the force F in the Cartesian vector. Look here, this is my XYZ axis and here is my 100 lb force. So the magnitude of this force is given to me and the direction is also clearly mentioned. That is, this force F, it makes an angle of 60 degrees with my XY plane, right? And it's also given that the projection of this vector onto the XY plane, okay, that is this line, it makes an angle of 45 degree with the x-axis, positive x-axis. It does mean that F is defined completely in terms of its magnitude as well as the angle's direction. So it is possible for us to express F in terms of the Cartesian vectors. So obviously we know that any vector, for example in this case a force vector, can be expressed in Cartesian format provided we know the components of this vector along positive x, positive y and positive z axis. That is, vector F can be written as fxi plus fyj plus fzk, fx, fy and fz being the magnitudes of the components of the vector along the positive x, y and z axis. So let us start working out the magnitudes of the components from these given details. So here the approach is very simple. So first what we do is that, okay, this is my 100 lb force. So first let us apply the parallelogram law first, okay, to obtain the component of this 100 lb along the z-axis and also along the xy plane. So as you can see, from the head of 100 lb, what I did is I have drawn a line parallel to the z-axis where it meets my xy plane, that is marked as f dash. Okay, this is the point where it meets the, okay, xy plane. So it does mean that this is my f dash, that is the component of f equal to 100 lb in the xy plane. Similarly, from the head of 100 lb, draw a line parallel to the xy plane, that means parallel to this line, where it meets the z-axis provides you the fz component. So this is the first application of the parallelogram law. So from this application, first application, it is very easy for us to obtain, because as you can see that this represents a rectangle, not a parallelogram. This is a rectangle because we are talking about all these included angles being 90 degrees. Okay, so let us go for the first application of the parallelogram law. So the first application of the parallelogram law gives us fz as, simply using our basic understanding of the trigonometry, fz can be written as 100 into sine 60. And what is f dash? F dash, magnitude of f dash can be written as, it is 100 into cos 60. So we obtained f dash and fz. So we obtained f dash as a 50 lb and fz as 86.6 lb. Now, so we obtained only fz. Now let us apply the parallelogram law second time so that we can obtain the components along the effects along the x and y axis. So what we do is that the vector that we obtained f dash in the xy plane, that is again resolved along the x and y axis. So what we do, from the head of f dash we draw two lines parallel to the x and y axis in order to obtain the respective, what we call as the rectangle, okay, or it's a special case of the parallelogram, right? So we have all the angles available to us. So that's, for example, here this f dash, it makes an angle of 45 degrees and 45 degrees with my x and y axis, which means that my fx can be written as f dash cos 45 and fy can be written as f dash sin 45. So from the magnitude of the given vector and the angles, we obtained fx, fy and fz. Now it's a straightforward task. So it does mean that vector f, we know that fxi plus fyj plus fzk can be written as 35.4i, that is my fx, and what is fy, that is, look here. Now one very important thing I want to tell you is that any vector is its magnitude multiplied by the unit vector along its direction. Now looking into the component along fy, its magnitude is already obtained to us, that is fy is obtained as 35.4 lb. And remember that the unit vector in the direction of fy is directed along the negative y-axis. It does mean that the corresponding unit vector associated with fy is minus j. That is why we have used here minus 35.4j. Plus fz is directed upward. Okay, as you can see here, fz, it is directed upward. So the unit vector is plus k. So it is plus 0.86.6 k lb. So we have expressed the given vector in the Cartesian format. When I say Cartesian format, we have to express in terms of the magnitude of its component along the positive xy and z axis, namely fx, fy and fz, and also in terms of the corresponding unit vectors I, j, k. Now obviously we need to check whether these components calculated are correct. There is a shortcut. We know that if fx, fy and fz are the components of a given vector, its magnitude can also be obtained using the simple formula fx square plus fy square plus fz square raised to 1 by 2. So on substituting the values of fx, fy, fz, we obtain straight away f is equal to 100 lb, which obviously matches with the given value of 100 lb, indicating that the calculated components are correct. Now let us go for the computation of the direction angles. We know that the direction angles are the angles which any vector makes with a positive x, y and z axis. And now you know that the unit vector along any given vector u can be written as, for example, the unit vector along f can be written as vector f divided by its magnitude. right? So that is nothing but fxi plus fyj plus fzk divided by f. We know fx, fy and fz. Okay, so here I think there's a small mistake, should be fz only. So we have fx, fy and fz here. So it does mean that the unit vector along vector f can be written as 0.354i minus 0.354j plus 0.866k. Now we also know that for a vector, whose direction cosines are cos alpha, cos beta and cos gamma, cos alpha will be fx by f, cos beta will be fy by f, and cos gamma will be fy by f, fz by f, sorry. Which means that directly we can obtain the direction angles alpha as cos inverse of 0.354, beta as cos inverse of minus 0.354 and gamma as cos inverse of 0.866. Please remember that alpha, beta and gamma are the angle which the vector f makes with the positive x, positive y and positive z axis. Looking into this sketch, you can say that alpha 69.3 degree is the angle which f makes with positive x axis, and beta and gamma are directly marked as 30 degrees and 111 degrees respectively. Okay. So now let me finally take you to the other problem. That's the final problem. So this again is a very simple problem, and this provides you a simple way of obtaining or expressing a given set of forces in terms of the Cartesian vector coordinates and then proceeding for the analysis. So let me read the problem statement. Two forces act on the hook as shown in the figure. Specify the magnitude of F2 and its coordinate direction angles so that resultant force Fr acts along the positive y-axis and has a magnitude of 800 Newton. So this again is the same problem similar to example number 1. Only thing is that here one component is given, one resultant is also given. You are asked to find out the second component. So all in fact, all this first problem, second problem and the fourth problem, it belongs to one family group of problems, right? So this is the diagrammatic representation of this problem. For example, look here, this is a screw hook. Okay, this hook is subjected to two forces, that is F1 and F2. So in the problem, the magnitude of F1 is provided to us 300 Newton and its positions are directly defined in terms of the direction angles. For example, you can see that alpha is 45 degrees, beta is 60 degrees and gamma is 120 degrees. Now regarding F2, so one component is given to us, F1, its magnitude is given and its direction cosines are given. It does mean that we can directly express F1 in terms of the Cartesian format. Now we are asked, so the screw, that is this hook is subjected to another force F2. We are asked to find out the magnitude as well as the direction angles associated with the F2 so that the resultant of F1 and F2 has got a magnitude of 800 Newton and that this resultant is directed along the positive y-axis. Okay, so the problem is very simple to us. So first of all, we shall solve this problem simply using the Cartesian format. So we will express first the given force F1 in the Cartesian format. It is an easy job for us because in this problem we are given the magnitude as well as the direction angles. So let us go for, we know that vector F1 can be written as F1xi plus F1yj plus F1zk. Now we know that the component along the x-axis can be written as the magnitude of the vector into cos alpha 1. Similarly, the component along the y-axis can be written as F1 into cos beta 1. And the component along F1's the z-axis can be written as F1 into cos gamma 1. So we are given the magnitude of F1, that is 300 Newton, and we are also given the direction angles alpha 1, beta 1 and cos gamma 1. So we can substitute all these values of the direction angles to find that vector F1 can be finally put in the Cartesian format as 212i plus 150j minus 150k Newton. So look here, so we expressed F1 in the Cartesian format. Now regarding F2, we need to find out what is F2. So let us assume that F2, let us say that it can be expressed in the Cartesian format as F2xi plus F2yj plus F2zk, where F2x, F2y and F2z are the magnitudes of the components of F2 along the x, y and z axis. Now coming to Fr, we are directly given the instructions for its magnitude. It is 800 Newton, and also it is given that it acts in the positive y-axis. It does mean that Fr can be straight away written as its magnitude, that is 800 into the unit vector. What is the unit vector along the positive x-axis? Along the positive y-axis, it is j. So we have expressed vector F1 in the Cartesian format, vector Fr in the Cartesian format. We need to find out what is F2. So substituting the value of vector Fr, vector F1 and vector F2, we obtain an equation of this format. Look here, on the left hand side, we have got the coefficient of I is 0, the coefficient of j is 800, the coefficient of k is 0. So we also have the coefficients of I on the left side, coefficient of j on the left side, coefficient of k on the left side. So we can equate the coefficients for ijk on the left and the right sides. We obtain three equations which contains unknowns f2x, f2y and f2z. So these are the two equations. That is, for example, if you equate the coefficients for ji, we obtain 0 is equal to 212 plus f2x. And on equating the coefficient for j, we obtain 800 is equal to 150 plus f2y. And equating the coefficient for k, we obtain 0 is equal to minus 150 plus f2z. So from these three equations, we obtain the components of F2 in the positive x, y and z directions as F2x is equal to minus 212.1 Newton, F2y as 650 Newton and F2z as 150 Newton. So having obtained the components, obviously we can straight away calculate the magnitude of F2 as a square root of Fx square plus Fy square plus Fz square, that is 700 Newton. Now we also, this is only the magnitude. We need to obtain its direction in terms of the direction angles. The direction angles of F2 can be obtained as cos alpha 2 as what? Fx by Fx2 by F2, that is minus 212.1 divided by the magnitude is 700. Similarly, cos beta 2 can be written as F2y divided by F2, that is 650 divided by 700, and cos gamma 2 is 150 by 700, which means that alpha 2 is 108 degrees, beta 2 is 21.8 degrees, and gamma 2 as 77.6 degrees. And these results are shown in figure B. So figure B provides us the correct details of F2 which is requested in the problem. As you can see that it has got a magnitude of 700 Newton and all the direction angles are given. For example, F2, it makes an angle of 108 degrees with the positive x-axis, an angle of 21.8 degrees with the y-axis, and an angle of 77.6 degrees with the positive z-axis. So that's all regarding this class. We'll go with a new topic in the coming class. Thanks a lot.